Good morning to one and all. I am Parthiban working as assistant professor in the Department of ECE. Now I am going to talk about the subject called electron devices, which is coming under the regulation R 2025. The subject code is EC25C01. Now I am going to talk about the unit 3, under which the subtopic is common collector. So CC mode is also a famous mode in the transistor configuration BJT. So CE, CB and CC. Earlier we have seen about the common emitter as well as about the common base. Now we are going to see about the common collector connection. So in this circuit arrangement, the input is applied between the base and collector, while the output is taken between the emitter and collector. The collector of the transistor is common to the both input side as well as to the output side. Hence the name that is called common collector connection. You see from the diagram, the first one depicts for NPN transistor, the next one depicts for PNP transistor. The input signal is applied between the base and as well as the collector, whereas the output signal is taken from the emitter and collector. You see similarly for NPN transistors, the input is applied between the base and collector, whereas the output is taken from the emitter and collector. Hence the name common collector connection. So the common collector, the amplification factor is depicted in the literal gamma. So the gamma is nothing but the ratio between the emitter current to the base current. So it is the ratio of change in emitter current to the change in base current, that is known as current amplification factor in the common collector mode, which is called as gamma. So the gamma value will always be less than 1, because the change in emitter current is almost equal to change in collector current. So in this mode, the voltage gain is always less than unity, we can say. In the next, we are going to see about the expression for the collector current. The collector current can be expressed in many ways. Here, IC is equal to alpha IE plus IC B naught. So collector current is nothing but the emitter current minus base current also, we can say. So IE can be defined in many ways. Here IE is equal to IB divided by 1 minus alpha plus ICB naught divided by 1 minus alpha. So the common collector mode is very popular because it is having a very high input resistance and very low output resistance. Due to this, the voltage gain provided by the circuit is always less than 1. This type of configuration is particularly used for impedance matching, or we can also say isolation purpose, so that it will avoid the loading effect. So this is seldom or very rarely used for amplification purpose, but it is very widely used because of the very ideal feature that is called a favorable feature also, that is having a very high input impedance and low output impedance. This is particularly meant for impedance matching purpose for driving the low impedance load from a high impedance source. It will ideally act as a very good isolator configuration. So this diagram depicts the complete common collector configuration with respect to the input side as well as to the output side. As we all know, in the input side we are connected with the ammeter and voltmeter. So by varying these two parameters, one voltage, another one current. For example, here VCB versus IB on the input side, we can able to study the input characteristics. By varying the VC versus IE characteristics, we can able to study the output characteristics of the CC mode. So in the next diagram, we are going to see the characteristics of CC mode, particularly both in the input side as well as in the output side. In the input side, you see it is a variation between the VCE versus IE. If you vary the IB, you see when IB is 0, it will have a low emitter current. When IB is equal to 100 microamps, it will have the high emitter current. It will be around 6 milliamps. So by varying IB, we can able to vary the characteristics. In the output characteristics, which is nothing but the variation between the VCB versus IB, you see the variation with respect to VCB. You see when VC is equal to 2 volts, it will have a less value. When VC is equal to 4 volts, it will have higher value. So the variations can be done by means of varying the VC. So these two diagrams depicts clearly the characteristics variation of common collector. So for the input side by varying IB we can able to vary the characteristics. In the output side by varying VC we can able to vary the characteristics. Here is the overall comparison about the three types of transistor configurations. One is CB, another one is CE, another one is CC. With respect to input resistance, CB is low, CE is low, whereas common collector is very high. With respect to the output resistance, CB is very high, whereas CE is high, whereas CC is very low. In terms of voltage gain, that is an important parameter. For CB, it will be around 150. For CE, you see it will be around 500. For CC, it is less than 1. So where we can use the CB, CB is meant for high frequency applications, whereas CE meant for amplification purpose, that is audio frequency applications, whereas for CC can be used for impedance matching or isolation purpose. You see the voltage gain, so it will be for CB it is less than 1, for CE it is high, for CC it is okay. So these are the things that we can observe. So based on the values we can use the transistors in the common mode or common base or common emitter mode. So based on the typical values we can select. So if you need a high current gain or if you need both high voltage gain and current gain, we can go for CE mode. So similarly for impedance purpose, we will go for CC mode. Similarly for high frequency application, we will go for CB mode. So these are the things that we can choose from. So you see here how a transistor can act as an amplifier in the CE mode. You see the input signal applied, you measure the amplitude and you see the output that is taken from the collector resistance, that is on the output side of the CE configuration. You see the enlarged sine wave. So with this amplification, so this indicates the nature of amplification done by means of CE mode, because it is having a very good voltage gain. So that's why it is having a faithful amplification of the signal. As I already told you, the transistor is operated in three regions, namely the cutoff region, the saturation region and active region. So if it is acting as an amplifier, we will use the active region only. If the transistor is acting as a switch, then we can use the region called cutoff region or saturation region. So this diagram clearly depicts the three region operation of transistors. So saturation region is nothing but is also called on state of the transistor, whereas cutoff region is called off state of the transistor, whereas the active region is nothing but the amplification region. So we have to select the Q point. Based on the exact Q point, we can able to get the faithful amplification of the signal. So there are three important parts are there. So the cutoff part, the active part and the saturated part. So these plays a very vital role in deciding the characteristics of the transistors, whether it can be used for amplification purpose or it can be used for switching purpose. So this diagram depicts the first one is for active, the next one how it is acting as a cutoff. So the third one is we can, so it is acting as if like a closed switch. So the third one is on state, the second one is off state, the first one is active state. So the first one can act as an amplifier, the second one can act as a cutoff switch, the third one can act as a on state switch. So this transistor configuration provides a linear amplification of the input signal. So that's why these small signal amplifiers are mostly classified as linear devices. These are the various references that I used to take the slides. Thanking you one and all for hearing my lecture very patiently. Once again, I am thanking you everyone.